Okay, let me just ask you a quick question. Now, that example you were looking at. Okay, so we've got a question on just exactly what we're going to work on today, and at least one person has a test coming up and a class that I don't teach, but the assignment you have in that class looks almost identical to the assignment I have, so. It goes into a little more detail than what I've assigned for this course. So let's just dive into it. Okay, first of all, it's got a bacteria culture. Okay. And I'm not going to use the same numbers you got. I'm just going to make up some numbers here, maybe a reasonable number. Okay. And let's say you've got 50 milligrams, and I don't know how you'd actually weigh a bacteria culture, because you are providing it with nutrients and there's evaporation and all kinds of stuff. And you probably look at the area covered by the culture as opposed to the milligrams. So this is not necessarily a realistic way. So if you're trying to keep track of the bacteria culture in your refrigerator, something you're going to eat, well, you wouldn't actually be measuring that. You just be careful about refrigeration. Okay, anyhow, you have 50 milligrams at 9 o'clock a.m. and you got 70 milligrams at 5 p.m. Not an unrealistic scenario, okay? And you're asked to find things like doubling time and initial value, okay? So I'm going to say milligrams measures mass, not weight, although sometimes we talk about it as if it does. You got physics in your future, you might as well get used to the difference between mass and weight. Okay, grams, 10 kilograms measure mass, although even physicists have gotten in the habit of saying it has a weight of so many kilograms. They talk about the weight of a star. Weight only occurs in the presence of a gravitational field. We can't bring a star to Earth. That would be bad for the Earth. Okay, and weigh it with our gravity. So just a little aside there, something you kind of want to get used to, but you will when you get to physics. Okay, so the question now is, what is a mass at midnight? Okay, there are other questions. What's the doubling time? What's the mass tonight? At midnight. Now, first thing you want to understand is this is growing exponentially. That's kind of given in the equation. That's the way populations tend to increase if they have enough space and enough nutrients. Okay. So, kind of a universal phenomenon that given ideal conditions, populations increase exponentially, because the more organisms you have, the more reproduction will produce new organisms. So if you got 1,000 people who produce, whose population grows at the rate of 20 per year, if you had 1 million people, that's 1,000 times as many. You'd expect them to grow at 20,000 per year. Okay, just expect the growth to be proportional. Okay, so I'll make a note. Already using the wrong words here. If I do that, even though I've had enough sleep, okay. But, sorry, my handwriting is very good here. Just make sure I'm still, make sure everything's visible. Okay. Because the increase in population is proportional to the population, we expect exponential growth. So that means we expect y equals some number a times b to the t, because that's what an exponential function is. And we know how to construct a graph with the shape of an exponential function. Okay, so we simply sketch the graph. Representing a typical exponential function. Now, what I did there is I sketched the graph of y equals 2 to the x, but I didn't label the axes because y equals 2 to the x isn't going to fit this. Okay, it's going to be y equals some other number to the x or to the t. And I'm using t here because we're talking about time. Okay, so t is here, y is here. So here's your picture. Now, I'm going to put the going to do another graph, and I'm going to put 9 a.m. 50 milligrams. Okay, well, we measure t from midnight, so t is 9 here. Okay, and t is going to be 17 here. 17 hours after midnight, that's 5 p.m. Okay, midnight to noon is 12 hours, and 5 more hours is here. 12 and 5 is 7. Okay, so we have, I'll put 9 a.m. here, and 5 p.m. is 17. So if 9 is here, 17 is, oh, maybe about there. And we try to do this to scale. And if I'm doing this to scale, I'd say, well, if we put 18 here, that's twice as much as 9. Then 18 is going to be double 9, so it'll be here a little to the right of 17. History class, playing all these tapes from my teenage years. Okay. Oh, yeah, I don't feel like I'm old enough to be part of history, but maybe I am. Okay. Not a very significant. Okay, so we got 9 and 17 now. At 9 o'clock, our population is, or our mass, our measure of population is 50. So I'm going to put 50 here. Now 50 is here, then 100 goes here. So I want to make a reasonably accurate graph. So 50 is here, 100 is here. And at 9 o'clock, I've got 50. And well, it's not 17 o'clock. Well, on a 24-hour clock, it would be. But when t equals 17, we've got 100. No, we don't have 100. We have 70. Put 100 there. Like I say, you got to watch it. Here's 7. So we're going to have a point about here. Okay, so what does our exponential function look like? Well, it can't start down here because it starts down here. It's gonna have to go up and it's gonna be too steep. It's not gonna hit this point. Okay, so it's gotta start a little higher. It's probably gotta go through the x-axis, maybe about here, or the y-axis. Okay, so it's maybe gonna look something like this. So if you draw a curve that represents an exponential function, it looks like this function is going to double. Well, it doubles, it goes from 50 to 100, right? Here it's 50. Here it's 100. Okay, here's your doubling time. Now, this is 9, here's 18, here would be 27. So I could put 18 here, I'm not going to, but I could do 9, 18, 27. I'm going to say 27 is about here. Just labeling multiples of 9. And I'm going to estimate that the doubling time, well, what's that look like? If this is 17 and that's 27, then what's that coordinate? And how do you calculate it? What in my picture? What would be the length of that arrow? Because the length of that arrow represents the doubling time. How long it took it to double. How are you going to use the numbers you see up there to estimate the doubling time? Yeah. Well, we don't want to take too long on this. So. And if you're copying down what's on the board, stop for a minute, digest this, and see if you can write down the other equation. Then go back to copying if you need to. Your brain just won't go there. Okay. But if you get it to go there, stop and write out the other equation. Or at least think hard about what I just did and what you need to do. I think you was you got the subject. What's that second point? Well, you wrote down an equation here, right? And you wrote down my equation, if you did put either side of it, okay? Now I used 9 and 50. What are the coordinates of the second point? What's the green point there? You've almost got it. What's T and what's Y then? And this what goes in. Okay, okay, here's your equation, right? You're gonna put y in here, and you're gonna put t in here. Okay? So what's y and what's t for the second point? Yeah, I see. Uh-oh. I don't think I stopped the recording. Okay, well, anyhow, I don't think anybody said anything, so I think we're all right. Okay. So question again is this is somehow challenging. You've got this, okay? So let's put a big reddish box around this equation. That's what you need to focus on. This is the equation we're using. And we're plugging the y and t value of this point in here. So that y equals AB to the t, I'll put a box around that again, becomes this because y is 50 and t is 9. Now, from this point, what's y? It's 70, right? The point 1770 T is now 17 and y is 70. So we get 70 equals A times B to the 17th. Okay, so now we have two equations and the two unknowns, B and A. We can solve these equations, and it's fairly easy to solve these equations. Find A and B. Once we find A and B, we can answer all the rest of these questions. Well, there's a little work to get the doubling time, but process here. Okay, let's go with this. Okay, so now we have the system of equations of 50 equals A B to the 9th, and 70 equals A B to the 17th. Solve for A and B. How do we solve for A and B? We use substitution. We solve the first equation for A or B. And then we're going to plug that solution into the second equation. Now, would you rather solve this equation for A or for B? Think about it for a second. Which is going to be easier to solve? For which variable is it going to be easier to solve, A or B? Okay. How many think A? How many think B? Okay. It's 2-1 and the 2 wins, because if you try to solve for B, you're gonna have a B to the 9th and you're gonna have to pick a 9th root. Or 1/9 power, okay? And we're eventually gonna have to do that. And it's really 6 of one, half dozen of the other. Because we're not gonna be able to avoid having to take a root, but right now, it's really easy to solve for A. We just divide both sides by B to the 9th. We choose A. So our equation is (50) equals AB to the 9th. To get A, we have to divide both sides by B to the 9th. So we get right here. Okay. If we divide both sides by B to the 9th, we see we're going to have a B to the 9th over B to the 9th there, and that just gives us 1. So we're just going to have A on this side. And we get A equals 50 over B to the 9th. Okay, so now plug A equals 50 over B to the 9th into the second equation. Second equation is A 70 equals AB to the 17th. And that becomes 70 equals 50 over B to the 9th. Times B to the 17th. Notice we've only got one variable here, B. So we can solve this equation for B. So we're going to simplify. And solve for B. Well, we have 70. This could be written as 70 equals 50 times B to the 17th over B to the 9th. If you wish, make that 50 over 1 times B to the 17th over B to the 9th. But B to the 17th over B to the 9th is what? It's what power of B? I'm going to ask you to show me with your fingers. As soon as I manage to mute. Okay, now B to the 17th means what? I think most of you got it. It's 8, but why is it 8? Okay, first of all, it's 8 because the rule is if you divide B to one power by B to the other, you subtract the powers. Why is that? It's because B to the 17th means a string of 17 B's, and B to the 9th means a string of 9 B's. These 9 B's can match up with 9 out of the 17, leaving you 8. Okay, if you match up 9 of these with 9 of these, you divide them and they give you 1. So they go away. Okay, so anyhow, you have to know this rule. And you see the rule, which says this should be B to the 17 minus 9, you got to remind yourself of why that rule works. Because if you don't reinforce the rule, you're going to forget it. And pre-calculus students are famous for forgetting this rule of pre-algebra. Okay? Or at least algebra 1. Because it's easy to mix up this rule with the rule for like a power to a power. So the rules can be a little confusing if you don't remember why they work. Which is why I wrote a remediation exercise that holds your nose to the ground. And hopefully enables you to nail this whole idea. So if you want that exercise, I can make it available. Let me know. Okay, so anyhow, you do have the rule, you have to apply it, you have to know these rules. Okay, so we then have 70 equals 50 b to the 8th. And you have to know this immediately when you see this, you know, okay, I subtract the exponents. Why do I subtract the exponents? Well, because I can match up 9 of these, and they divide out. Okay. You really have to think that immediately when you see any something like this. Otherwise, you get hung up and you're going to be very error prone. Okay. So you got 70 equals 50 times b to the 8th. What do you do next? Well, write out that 70 equals 50 times b to the 8th and write out your next step. Everybody wrote this down. It took some people, 2-3 minutes to write the next step. It's got to be done in 2-3 seconds. Plus whatever time it takes you to make the strokes and take. So if you can't do this immediately, if you have to stop and think too much about it, you need drill and practice. Okay. And I've got a good drill and practice for solving linear equations. They don't solve this time, but they get used to when you multiply both sides, but not divide both sides. And they tell you whether you're right or wrong, and they tell you the right answer if you don't have it. Okay. So I kind of recommend that. And so if you want to look at that exercise, I think there are 8 problems. You're supposed to do them, and it's times how long it takes you to do it. Okay. And they're, they take a little while. It might take you 30 minutes to do the 8 problems if you're writing them out. And if you're not efficient, it might take you all day. Okay. If it takes you all day, you need to get that time down to like. You're doing the 30 minutes, it's kind of okay. Some of them are a little more complicated, some of them are really easy. So email me if you want me to put those on. I can copy them into your open math. Probably into, well, I can copy. And they become available. It just takes me a couple of keys. Okay. Okay. So I don't want to put it there and clutter up the open math unless you're going to use it. So email me. Okay. Okay, anyhow, you have this. You're going to divide both sides. Actually, I think at least one person had the b to the 8th over on this side. It's over on this side. You're going to divide by 50. Because that's how you get rid of that 50. You undo this multiplication by division. Okay, well, that gives you then b to the 8th equals 7/5. So we got b to the 8th equals 7/5. What do we do with that? We've got to find b, right? We need another law of exponents. Okay. Now I usually do this just by exponents if I want to reinforce the exponents. And I personally always found it simpler to do this than to deal with radicals, but I could deal with radicals very easily too. To do it one way, I'm going to write it this way. We could write the 8th root of this equals the 8th root of that. Okay. That adds an element of mystery, but it is a convenient thing to do. But why do you have to use that radical? You don't. You can use exponents. It's easy to understand what happens with exponents, and you need to understand the rules for exponents. So we need to understand that b to the 8th to the 1/8 is b to the 8th times 1/8, and that equals 7/5 to the 1/8. Okay. Then 8 times 1/8 is 1. Again, that's 7/5 to the 1/8, which I think is about 1.04 by the rule of 72 in my case, or 70. Maybe I've got that wrong. I know how to test it, okay? I can test which one fits better for growth rates in the order of 0 to 0.1. So, okay, well, anyway, you solve this, you get this, you don't know how to estimate it. Okay. And I use the rule of 72 to get the doubling time, because I think the doubling time is around 18. It gives me a growth rate of 4%. Okay, so I think we get B approximately equal to 1.04. You get that? Yeah. Okay.
Okay. And now,
Well, now we know B. Now, that's something, all these steps, you should be able to do, because the steps themselves, without all the explanation, this gives us this, which gives us this, and finally this, and this. Okay, well, that's several steps, but each step is really short. And if you practice this, you can get this down very quick. Okay, well, now we've got B. Okay, how we're going to get A? Well, we're going to get A easily enough. If we know B, we've already solved. And if we solve this correctly, A is just 50 over B to the 9th. Okay. So what's A? A is 50 over B to the 9th, B is about 1.04. Well, then A is 50 over 1.04 to the 9th. And that's approximately 35. Now, with your calculator, you get better estimate, more accurate. Okay, but since this is bacteria growth, it's probably close enough to estimate when you better not eat that turkey in your refrigerator left over from Thanksgiving 6 months ago. 5 months ago. Okay. Make sense? Well, just to complete it now, we found A and we found B. What's our exponential function? Well, our exponential function is y equals a b to the t. So we went to all this trouble. And remember what we did. We took our information and we put it on a graph and we estimated. That orients you to the problem. And it only takes seconds. You know, you can slap down a graph with some numbers here in less than a minute. And if you do it for, 15 problems and put the stuff on a graph and make your estimates, you're going to get pretty quick and pretty good at it. And it reminds you then of what you do. You take each point, you identify the form of the function. And in the case of the assignment you're working on, or we'll be working on for next time, because that's, I think, what we got. Okay. Or a test you have coming up. It's always going to be this, or maybe an e to the KT. Okay. If it's an e to the KT, it's a little more complicated. In that you got to use your conversion between logarithmic and exponential form to find K. Here you don't. Very simple. It's simple algebra, nothing new. But the e to the KT, we'll do it with the e to the KT, but I'm going to go through it quickly. Steps are almost identical to what we did here, except there's a step where you have to go from exponential logarithmic form. Solve for K. It's not hard. No, really no harder than this. It's an alternative. So there's your function, or it's a e to the KT. Okay. Equivalent. And you should understand that those are equivalent. It's just a vertical compression or horizontal compression. No, you know, that's what K is. Okay, that aside, what's our model now? Even when you do it, you're going to find that y equals 35b to the t, yeah, 35 times 1.04 raised to the t. This is our model. Again, we put our information on a graph, orient us, we make an estimate or a doubling time to see if, you know, our result makes any sense. And it doesn't have to be that good of an estimate, but it's going to give us a ballpark if we know how to sketch an exponential curve. Mine was a little too steep. So I got like 15.5 when I should have gotten maybe 17.5. We'll see in a minute. We'll use our model to do this. Okay. Critical thing is take your data, get your model. Plug your data in. You need 2 points to solve for A and B. And if it's A e to the KT, you got to solve for A and K. Okay. Either way, you've got two equations you have to solve by these methods. Give us a model. Okay, so where are we? Okay, so our model is okay. That's a whole lot like compound interest. Okay. We're multiplying by 1.04 each hour. Okay, so our growth rate is 4%. Every hour, we have 4% more bacteria than we had the hour before. Okay, what's 35? Well, let's answer a couple of our questions, okay? What was calling this? Yeah, the way I wrote it down is what was the mass at midnight? Since I've got two midnights, one is the midnight where we started our time, and the other's the midnight tonight, okay? So this midnight of the day we're on, down to midnight of the next day. So I'll call that the last midnight. Well, what's T? At the last midnight, okay? You show me with your fingers? No. No. Okay, if we go back to our information, that's what was the mass at midnight, okay? Now, our time is 9 at 9 a.m., and it's 17 at 5 p.m. What was it at midnight? Zero. Yeah. We're measuring from midnight, right? If T is 9 at 9 a.m., it was 0 at midnight. Okay? If that's not clear, go find a clock, round clock, and study it. Okay? You can see that. And it might be that, you know, y'all grew up with digital clocks in your school. I spent all my time watching the round clock, not the digital clock. Okay, so I got familiar with it. I don't know how students understand time from digital clocks. I don't think you understand time unless you see the hand going around. I find it criminal if schools install digital clocks and save money. Okay, or maybe they think that that's a good thing. Maybe they have a point. I don't know. I can't conceive of the whole thing of a circular model is you don't know how important that is in mathematics. It goes way beyond just being able to understand time. Okay. Basically, you need to understand the universe, and you'll find out if you really need to know. Okay. Okay, so mass at the last midnight, T was 0 at the last midnight. That's the 0 point of your graph. If you look at your graph here, this is 9 a.m., this is 5 p.m. What do we get if we count backwards from 9 a.m.? 8, 7, 6, 5, 4, 3, 2, 1, 0. Right? You can also understand it linearly, you know, on a graph, and people need to understand graphs, all right. You could have, never mind. Instead of clocks, you could have a little dot moving along the graph. That would be beneficial, but probably not. Okay. Okay. So T was equal to 0 at our last midnight. Now, what's the first question here? It was, what was the mass at midnight? T is 0. Okay, here's your model. There's T. T of 0, you put in T and you do your calculation. It's an easy calculation in this case. T was 0, 1.04 to the 0 is 1. So that just equals 35, and there's your answer. Now you probably want to use a calculator. I don't know how much wiggle room open math is going to give you for a problem of this nature. There's usually wiggle room. But I had to look at the code for that problem, so I don't know how much wiggle room there. And I'm not going to look. I'll write my own problems and decide on my own wiggle room. Okay. So what's the doubling time? Well. Well, this is pretty unfortunate. It's really unfortunate because it contradicts a lot of stuff I expect. Coincidentally, if this is 35, your doubling time turns out to be 17. Okay, because starts at 35, this is 35. That looks about right, doesn't it? If this is 50, 25 would be about here. That's very plausibly 35. So we got new information. But if you double 35, what do you get? You get 70, right? Well, we happen to have a point where this thing is 70 at 17. Okay. So I'm going to change my 35
to whatever you got using your calculator, so we don't end up exactly with a doubling time that totally matches our graph. I just made those numbers up without thinking, and it's very convenient that 70 over 50 is close to the square root of 2. I didn't intend it that way, and that kind of throws a hamper into things. So let me correct that number.
Okay, well, it gets even worse. If I correct that, I get 35.1 something. That's ridiculous. So hang on a minute. We got a comment from the messenger here. Okay, now we have an unfortunate and unpredicted glitch in our numbers here that tells us that if 35 is the correct number here, then our doubling time is exactly 17, and we don't really have any work to do. Now, remember, we estimated 15.5. I said it's going to be close to 18, and I said maybe 17.5. Turns out to be pretty close to 17. Could be a little closer to 18. So if we do something a little more accurate. So our model back wherever we did it. If that B is about 1.04, I'm going to change that value. 1.043 is closer. Again, I use the rule 72, or maybe I should use rule 70, whatever. And then this calculation would have a 4.3 in here instead of a 4, and that would change this result to something that's closer to 34. So, as long as my moisture here holds out where it is, I change this to 34. Then, of course, where to put it? Cover it up. Yep. Okay, so my 35s here become 34. It's actually like 34.2 or 34.3. That came from the calculator. Didn't try to estimate it that closely. If I had, it's not clear that I've done very well. Okay. So now let's calculate the doubling time. It's not going to come out exactly 17, so we can illustrate the process without $4. Okay. Okay. Y is 34 at t equals 0. Double this mass is 68. Actually, it's gonna come out a little bit less than 17, okay? My 17.5 wasn't great. Okay, we double this mass, it's 68. We're gonna solve y equals 68 for t. Of course, there's no t in this equation. Well, since y equals 68 means that 34 times 1.043 the t equals 68, and the solution you get there is going to be the time it takes to double. Now, on the graph, what this means is we've determined that this value here should be about 34. If we double 34, here's 68. Okay. On the graph, it looks like that's going to occur approximately when t equals 16. You might think that's 15 or 15.5, but what I drew it there looks like it came out about 16. So by drawing it on the graph, you reinforce why you're solving this equation. Well, solve this equation. You should know how to solve this equation. And if you don't, of course, I'm going to help you. Okay, so we want to get to t. First thing we do is we divide both sides by 34. We don't subtract 34 because 34 is multiplied by this. Okay. We get 1.043 to the t equals 2. Now where are we? What are we going to do with that? What have we been doing in this chapter? Okay. Now at this point in this chapter, we've solved a bunch of equations of this nature. Okay. So we might want to go back and look at how we solve those equations. And hopefully we recognize that this is an exponential equation that needs to be converted to logarithmic form. Okay. This is in the form well, let me use the form that I used in this class. Very close to the form that you've seen in Open Math. Except I want to reserve B, the letter B for the base. It's the form B to the A equals C, where A and your exponent. Same equation in exponential form is log base 1.043 of 2 equals t. So now the form is this. And this left-hand side is something you can get from your calculator. So now T equals log of 2 over the log of 1.043. Now, if you're on a test and you want to use the ability of your calculator to do a log to a base without actually using an important rule, do it on a test. But if you're doing a problem of your own, I really recommend that you write it out this way. And then you can check it against what that calculator shortcut gives you. Okay, so one way or another,
What do you get? Is it closer to 16 or 17? Well,
so we got about 16.4. And this is a doubling problem. This is the time. Y equals 34. Y equals 68. Okay. Now, what's the mass going to be tonight at midnight? Somebody will tell me
what T is at midnight tonight?
okay, well, if midnight way early this morning was 0, midnight tonight's going to be 24, isn't it? So Y equals 34 times 1.043 to the 24th. Okay. Now I can actually do an estimate of that on the graph. 24, well, that's 24.5, that means 100. So it looks like we're going to be close to 100. Okay, so if this is 24 and a half, 24 will be a little less than that, it might be 96. 103.
93.
Okay. So I might have done a really careful job on that graph. I might have come out with 93. I just picked the number, 96 wasn't too bad. Turns out it's 93. Okay. Now, you probably want to see it done with AE to the KT. So I'm just going to write it down real quick and say what it is. It'll take me about 2 or 3 minutes. If you want to stick around for that, please feel free. If you want to take a break, well, class is over. Just go out in the back rather than in front of the camera. Okay. Okay, so. Doing the same thing we did using Y equals AE to the KT. The steps are going to be very close to what we did. We're going to get. What is it? 50 equals AE to the 9K. Because it's equals 9, Y was 50. Then we have 70 equals AE to the 17K. We solve for A. Now I'm going to use arrows in the first equation. We get A equals 50 over E to the 9K. We take that value and plug it into the second equation, and out of that, we get 70 equals 50 over e to the 9K times e to the 17K. So we'll put that over 1, but we understand then we could put the 9K here and the 1 here, and e to the 17K over e to the 9K is e to the 8K. So that's 70 equals 50 e to the 8K. Okay, so we've got 70 equals 50 e to the 8K. So we got to solve for K. Now, we see that this is an exponential. The thing we're trying to solve for is in the exponent, right? So we're going to have to put this in the form e to the a equals c and convert it to logarithmic form. So we solve this, we get e to the 8K equals 7/5. We divide both sides by 50. I'm not writing out that step. Okay. So then we get log to the base e of 7/5 equals 8K. So the K equals, and log in the base e is a natural log, so that's a natural log of 7/5, okay? Natural log is 7/5 over 8. Okay, which is approximately 0.04. Okay. And that's because the trail expansion, they're exponential, and we don't want to talk about that. That's second semester calculus topic. Okay. So there's our K. And yeah, that's right. So now A is AE to the 9 times 104. That comes from this equation where we substituted the value of K right here. And now we solve for A. A is going to be 50 over e to the 3.36. And that's approximately 34. It's the same numbers, but we do have this need to solve an exponential equation when we use the exponential form. So we get y equals 34 e to the 0.04t. E to a very small number is pretty close to 1 plus that small number. That just comes from something you learned in second semester calculus, not something you want to use right now. Okay. But that checks it to my satisfaction. You can check it out and see if losing half a night's sleep really deprived my brain or helped me focus. Because I'm much better focused today than I was yesterday. Okay. Any moron can put their problems up there. And other morons can use them, okay? But this moron is keeping his problems private so nobody else can use them, so I don't ruin anybody's life. Okay, And eventually I'll see what the problem is working. I'll contribute some of them because they're different than what everybody else is writing, but not at this point. Okay. Still in the system. So again, my point is, if you didn't do well on part of the homework that gave you a logarithmic graph and said, tell me what function this is. Well, I kind of care. I wish you would. Wish you could, but I'm not going to test you on it. Okay. I don't consider it to be important. Again, saying this on video, what I consider to be important is the ability to construct stupid graph, which OpenMath doesn't support very well. There's no way that you can assess a graph a student makes with their mouse. That's a terrible way to make the graph. Okay. It's a misuse of the technology and a limit of the technology. Technology doesn't really support constructing a graph. Okay. That said, we talked last hour about how you apply logarithmic functions, applications of logarithmic functions. As I said, I think people did well overall on the problems. I hope you did the problems in the recommended manner without sitting there looking at the next step on an example and imitating it. It's nothing really going into your head. Okay. In the programming, I'm starting to do with OpenMath. You know, I still, I'll tell it to do something, and it'll give me a rude gesture. Okay. No, it just doesn't always work because I'm not totally fluent with programming. Okay. You know, a couple hundred commands, a couple hundred things it does. They're all obvious, but do you remember exactly what the syntax is? Do you need a comma here? Do you need a parenthesis here? Do you need a quote? Okay, little stuff like that, just little stuff that I'll get fluent with fairly quickly. Now, the analogy is simply, you need to get fluent with what you're doing in the home, okay? To the point where you don't need to look at anything. So be sure you continue to strive for that. Okay. We're going to do an example of radioactive decay. So, and let's not do radioactive decay. I don't want to say let's do drugs. Let's do an example with drugs. Don't be doing drugs. You know, get hold of some fentanyl and kill you. You know, yeah, don't. I don't think you do. I don't think it is coherent enough to keep showing up for class. Okay. Okay, so let's say again, I'm as stupid, brain foggy, and unfocused as I was yesterday. And I take one of those prednisones that my allergist prescribed for me when he saw me at the gym. It's very interesting. He asked me how my allergies were, and I said, "Oh, dude, it was terrible." He said, "Yeah, it is terrible." Okay, I don't think I've ever taken it prednisone. I just don't like to take some. And I usually don't need it. But let's say I take one of those, 10 milligrams, okay? So, we're going to specify the drug. Now, we're going to assume that that drug gets into my bloodstream instantly. And that's not really so. But it probably gets in my bloodstream within an hour, so we'll just pretend it's instant. But we're doing a model, and the model is going to give us a pretty good indication of what happens. But the model can always be refined. Okay, well, the model is gonna be, now I could walk over to that computer. I could type in half-life of prednisone. ChatGPT, pop it right up, or most search engines will give me a link, and a lot of times I can see right there without having to even click on the link what the result is, okay? I'm not gonna do that. I'm gonna pretend it's 8 hours. Okay. Actually, I'm not. I could use the half-life, but I want to demonstrate how you calculate a half-life. Okay. So, data. Predicts that after 8 hours, 60 milligrams will still be in my tissues. Okay, so it'd still be acting, still suppressing the allergic reaction. Okay. Right there, we have everything we need to create a mathematical model of how much prednisone there is, of how much of this drug there is in my system, okay? At this point, as soon as we have this data, as soon as we know essentially 2 points on the graph, we can create an exponential model. Okay. There's a model we're going to use first, and then we'll do it with an exponential model. I mean, they're both exponential models. We use an exponential function, y equals a e to the kt. And so it's either a b to the t or a e to the kt. They're totally equivalent. If you know b, you can find k. If you know k, you can find b. Okay, very easy. Once you know how to do it. I'm going to put the information on a graph. Just gonna take a little note here. Here's Y. Here's T. And can you write down the coordinates of 2 points that are going to occur on a graph of Y versus T? That would be 2 ordered pairs to give me the coordinates of 2 points on the graph, given that information. Okay. Let's see if we have it. Let's see. Yeah. Look, the ordered pair, okay? In the world, right, world of black and brown. Okay. I'm gonna say at 0 hours, we got 10 milligrams, right? And we put the T coordinate first, okay? Put the hours first and then the milligrams. Okay, so T, you can label this, T's in hours. Y's in milligrams. And then we have 8 hours, 60 milligrams. So we put those points on the graph. 0, 10. And since we have labeled T in hours and Y in milligrams, we don't bother putting the hours of the milligrams here, but we still think about it. Then 8 hours, 60 milligrams. So let's see. Put 8 hours about here. Because maybe I'm taking one of these every 24 hours. And maybe one of them, and that's basically how it's described. Okay, so 8 hours, 60 milligrams. Now, if this is 10, then halfway between here and here would be 5. So you have 6, 7, 8, 9. So here would be 6. About 5, 15. No, it's more than 6. And okay, I was careless. I said 60 milligrams. Well, 60 milligrams would be up there and should be 6 milligrams. Okay. Go back to that one. That's the first real bonehead thing I've done today, so I'm having kind of blew that one. Okay. So there we've got 2 points on the graph. And it would be H6 rather than H6. Now, on the right side. Okay. Now, we want an exponential curve that goes through those points. It's going to be a decreasing exponential. So, can you sketch me something that looks like an exponential curve would through these 2 points? I can tell that the assignment people did for today made an impression because everybody's trying to draw a logarithm. Okay. Let's review exponential logarithm curve. You really need these pictures to be able to visually understand what's going on. Okay. First of all, your basic exponential function. And the graph that looks like this, right? Be a toolkit exponential y equals 2 to the x. What does y equal? Okay, that's an increasing exponential. This one has to be decreasing. How are you going to make this decreasing? You're going to reflect it about the y-axis. Okay. Decreasing exponential. Would be like y equals 2 to the negative x. So you have to draw a curve that looks like an exponential. It's got an asymptote at the x-axis. But it's got to be decreasing. It's got to go through these 2 points. So show me again what that's going to look like. And make sure you understand what I just said, because that goes back to the very first chapter where you transformed functions, reflected them. You know, replace x by negative x, it reflects across the x-axis, all those rules, which you're going to have to know for the final, okay?
Is really important stuff. Really important to get a picture of what's going on rather than just imitating algebraic steps. Okay, most of those graphs look pretty good. Okay, now one thing you don't want to do, well, is some of you drew it so it has an asymptote way above the t-axis. And the asymptote has to be the t-axis. Okay. So it's gonna have to go down here and approach the t-axis. So it looks something like this. That's not great. And I don't expect great, although some of yours look pretty close to great. Okay. Some of you have graphs that can actually be used to make a reasonable estimate. Okay, so what I want to do now is take that graph and estimate how long it's going to take this thing to fall to half. Okay. How long does it take it to fall to half its original value? Its original value is 10, right? If it falls to half, show me with your fingers. What's it going to be if it falls to half? It'll be 5, right? I don't know if it's just waving or if it's got 5 fingers up there. If you happen to be waving, I'm waving back, okay? So don't want to hurt anybody's feelings. Nobody's making rude gestures yet, so it's all right. Okay, now we're doing pretty well with this. I'm pretty good with the estimates. I don't think I've got a very good exponential curve there, so I don't think my estimate's going to be great. But it's going to be pretty close to 8 because it's already down to 6 here, right? So what we want is we want a point where this is the point where that's after the original Y value. We choose 5. Okay, so that this distance here is the time it takes to fall to half, and we call that the half-life. Half-life is this arrow. Okay. So according to your graph, where your graph crossed or the y equals 5 line, what do you estimate the half-life to be? Notice I drew this arrow here to indicate the half-life. Most of you didn't draw that arrow. Okay. I think it's a good idea to draw the arrow, if no other reason because you saw me draw it, but that arrow reinforces or is intended to reinforce the idea of a half-life. So how long is that arrow? And well, most of you have a good estimate. Most of you estimated. The most common estimate I saw was 10. Okay, my graph, I think that estimate would be more like 11 and a half. But I think my graph sucks. Okay, it's not a good graph. I think most of your graphs are better than mine. Because I just happen not to draw a very good exponential graph, but we'll see how it holds up. I think an estimate of 9 or 10 is going to be closer than my estimate of 11 and a half. I'm going to use that estimate.
Put a big question mark after. If I could make a bigger question mark, I would. I should have left myself room to make a question mark about that big, because that's what's appropriate to my estimate, which I think is a bad estimate. Okay. Well, let's find out what it is now. We've got a picture of what the half-life means. We've got a feel for how this stuff is gonna be processed by the tissues of whoever body takes this thing. Okay. So now, here's the exponential model. A, B to the T, or A, E to the K. Just like a 2 to the X or 2 to the minus X. Okay? But with a different base. And you should understand these bases because you did a problem where you had a bunch of exponential curves and you were asked to identify the base for each one. If that didn't make an impression on you, you should go back and look at it. Okay? If you need to understand. Okay, well, let's do the alpha. Y equals 10. T equals 0. So then equals A times B to the 0. Y equals 6. When T equals 8. So 6 equals A, B, the 8th. Got two equations. It's good that we have two equations because there are two things in this function that we don't know. We don't know what A is. We don't know what B is. We solve this system for A and B by the method of substitution, which is a method that you should have used fairly extensively in your algebra courses. It should be familiar to you, but I observe that it often isn't, especially in students who learn their algebra during the height of the COVID epidemic, which hopefully starting to, we'll stay kind of slacked off, okay? So hopefully things will improve. For sure, yeah. Over here, board is for long. Big more room. I'll start with it. Okay. So here's our system. So this should be reviewed. If it's not, I recommend that you watch the earlier part of this video where I did this in great detail. Because I'm not going to take the time to do it in as much detail. We want to look at several different times. Okay. And we also want to look at some simultaneous linear equations. You'll have that for Monday. Of course, there's only two. Yeah. Okay. Got these two things here. Okay. Well, B to the zero is one. So we just solve this for A. It's real easy to solve this one for A. Now, for the example we did in the support course, we had to do a little more work to solve for A. So either check out Open Math or check out that video. It's a fairly long video, but it goes into a lot of detail. And I pretty much don't make a lot of mistakes. Okay, which is really unusual. Getting half a night's sleep could be beneficial. Forces me to focus. Okay. Now, we got A equals 10. Okay, well, I plug that in here. And out of this equation, 6 equals 10 B to the 8th. Now, how do we solve 6 equals 10 B to the 8th? It's an algebra 1 problem. Okay, so it's something you've done, but during COVID, maybe not done quite the right way, where it really is something. So you got to get this the same way. The steps are simple enough. Divide both sides by 6. I'm sorry, divide both sides by 10. You know, trying to make this fair. Okay, so we divide this and we end up with B to the 8th equals 0.6. And how do we solve this for B? Well, you might remember radicals. You could do an 8th root. I prefer not to use radicals. I prefer to solve this equation one way with just plain old fractional exponents. Okay. If you like radicals, please feel free to use them. I think it's at this point unnecessary confusion. But it's something you really should know. I'm not going to do it. I'm going to do it this way. I can take the 1/8 power of both sides. Why is that? It's because B to the 1/8, B to the 8th to the 1/8 is B the 8 times 1/8. That's 0.6 to the 1/8. Well, B to the 8 times 1/8 is B to the 1. B to the 1 is just B. And everybody knows how to calculate 0.6 to the 1/8 in their head, right? I can't calculate that very accurately in my head. Okay. Let's see, 0.9, 0.81, 0.65. It'll be, I'm going to estimate that's about 0.9. Well, take your calculator and tell me what it really is. Okay, now I estimated that 0.6 to the 1/8 is 0.96 is a bad interpolation. 0.9 overdoes it. That would be. Okay. I know what I was thinking. But what matter? Okay, so B is about 0.9. Well, put a circle around that because that's all we need to fill in this function. Okay, so put this in red. This is where we start. We start knowing that this function is exponential for reasons that we'll talk a little bit more about, that this comes out. The more of this drug is in your tissues, the more your kidneys are going to figure out. Or the more it's going to be metabolized in some way or combined. The more of it's going to end up in the bacteria, which are going to end up dead, so they're going to get filtered out too. So, you know, you end up using up or excreting the drug in proportion to how much you have. You got twice as much, there's twice as much for your body to work on. Okay. That's what gives you the exponential function. Okay, so now. A is 10, B is about 0.94. Y equals 10 times 0.94 to the T. Now, incidentally, and you would have encountered this in earlier. Problems. This is, so it's the growth factor, and I like to call it the growth factor. So your open math calls it the multiplier, which is not a bad term. But I like the word growth because that's the basis of exponential functions, okay? Multiplier or growth factor is 0.94, which is 1 minus 0.06. Now remember, if you have 6% interest, your growth factor is going to be, or your growth rate is 0.06. And your growth factor would be 1 plus 0.06. Remember back to how we build up compound interest. Okay, every year you multiply by 1.06. And you'd end up with a 1.06 to the T. In this case, you're taking away 6% every hour. Okay. So this gets you close to the meaning if you understand compound interest, which you really need to understand practical purposes as well as mathematical purposes. You're not going to understand exponential functions and how they're applied and how they behave unless you understand these growth factors and growth rates and multipliers. And that starts with the model we use for compound interest. Now, you might have another model that you like better. The compound interest is something of that's easier to understand than a lot of other. So I recommend you really work to understand that. Okay, so that's it. We start with our information, our data. We recognize, or we know from physiology, or we take somebody's word for it, it makes a certain amount of sense, that the rate at which we get rid of this drug in our system is going to be proportional to how much drug we've got in our system. Again, if we have twice as much drug, we're going to take twice as much out. Okay. That results in an exponential function like a b to the t or a e to the kt. Decreasing exponential in this case, because obviously we're taking stuff away. Radioactive decay works exactly the same way. If we have radioactive element, we got 10 milligrams of it. 8 hours later, we got 6 milligrams. Well, then this model predicts how much radioactivity or radioactive element we have. Okay. And with radioactive elements, every atom has a certain probability of decay, emitting some radiation that might or might not be harmful, okay? In any given instant, okay, any given second. So it's like continuous compound, except it's continuous taking away. If you have only half as many atoms, then only half as many are going to be expected to decay in an hour. Okay, you only get half the activity, but you only have half the atoms. Each one still has the same probability of decay. That's something you kind of ought to think about that. Just deepens your understanding of what an exponential function is in the way that. All right. Okay, so again, assuming an exponential model, we can assume this or this. Either way, we sketch ourselves a graph. We put 2 points in the graph. That's a critical point that people don't want to do. Often because they see it done just with pure algebra in an open math video. Depends what videos you have, okay? I don't do videos for open math because I don't like their interface at all. And I'm not going to post my chalkboard videos. I think it might offend the, there's good reason for this. ADA compliance. You got everything's going to be good for people's disabilities. And if you have a disability, it doesn't allow you to learn anything from a great lunatic like me, then I don't know if that's an official disability, but there might be a disability that makes it difficult for you to see colors on the board, for example, colorblind. You're probably better off looking at the open math stuff, which doesn't use colors a lot, although they do use color. Okay. So I don't know how they get by 88 compliance with that, but they do their best. And so it's reason for their interface. I don't like their interface for my stuff. I like it. Math needs to be done by hand on the chalkboard. Not only this my preference. Okay. Aside from that digression, this is the process. Open math probably doesn't show you to sketch a graph with 2 points and make an estimate. I think it's an important aspect of learning to see what graphs tell you, and also giving you something to look at while you do the algebra. The algebra is representing what's going on here. If you have this picture, you're more likely to get the right equations. Now, once you've got the equations, then you got to do the algebra right. Okay. I did an example in the last class, and I run the videos together, so we actually get a fairly long video. I did an example of what you do with AE to the KT, which is very similar to this, except at some point you got to change from exponential to logarithmic form, which is something you should be very adept at. Okay. Because in like a little over 3 weeks, you have a final exam. Definitely going to have to do that. A lot of that. Once we have this, we can predict how much we'll have after 24 hours. For example. So let's say I'm taking this product, okay? And I've got let's say I've got some kind of bacterial infection. I need to take antibiotics, right? I take an antibiotic, let's say every 24 hours. It's got a long half-life, probably longer than this. It's got a shorter half-life. I probably take 2 doses. Okay. But let's assume taking 1 dose every day of this stuff. Let's see what happens. Okay. So This is Wisely Mountain Body in milligrams, T's time and hours. So now the question is. How much of this stuff remains at the next dose, which occurs in 24 hours?
Okay, can you write down the expression you would have to evaluate to determine this? We have the model and we have a question. So how does the information in the question fit into our model? What does our model tell us?
Okay, what's for my happiness? We've already got that. So. Okay. This is the amount after T hours. I'm writing out the logic of it, just to reinforce it. After 24 hours. Y equals 10 times 0.94 to the 24. Okay. Now. That's going to equal. I think 2.16. Anybody got a calculator can calculate that? Make sure that I'm not imagining things. You get 2.16. What does that say? 2.265 something. Okay, yeah, we got to round off. That 0.94 is not exact. Okay. If you use a more accurate version of it. Okay, if you calculate this. It would be 2.16 ideally, but the 0.94 is rounded. Now, how do I know that? Well, in 8 hours, we went from 10 to 6. Okay, in 8 hours, we got down to 60%, right? In another 8 hours, you're going to have 60% of that. Well, 0.6 times 0.6 is 0.36. And 0.36 times 6 is easy enough to calculate. It's 2.16. Okay. And I know first few powers of 6. Okay. And 6, 36, 216, 1296. Okay. Fifth power, I can do that in my head, but I have to think. It's not a good thing to do that. Okay. So that wouldn't be 100% certainty. So do we understand what this is telling us? One thing it's telling us is we get like 2.26. We use 0.94. If we use a couple more significant figures for 0.94, we never thought that they would give us that, then we come up even closer. That's worth knowing because in open math, you've got a certain latitude in your answer. Okay, maybe it wants 3 decimal places. Okay, that's kind of a standard, or three significant figures. But it's not universal, it depends on the person who wrote the problem. But usually there's somewhat, maybe it's within 1%. So you do want to be aware of that. If you round this off too soon, probably not going to get an answer that's as close to the perfect answer as open math is looking for. You probably already experienced that, and you probably know how to deal with that. All right. Now let's answer another question. What's the half-life of this drug? Okay, we estimated half-life. You all think it's 10. I don't think it's 11.5, but my model gave me 11.5. Okay. Right. Half-life is completed when T is 0, when Y is 10, right? So this little parenthesis T equals 0, and that's when Y equals 10, and T for Y equals 5. Okay, I would say when. Okay, well. If Y equals 5 now. Times 0.94 and T equals 5. Now that's a very typical exponential equation. We solved several of them in class. You solved a bunch of them for homework. Can you solve this one? Kind of test whether you retained it from homework and alerts you to the fact that you better review if you don't remember how to do this. Okay, so you got to put this into our b to the a equals c form. That's how we solve the exponential equation. And it's not in that form. But if we divide both sides by 10, it will. Now, I know that you have a bunch of equations that you need to solve. Okay. By putting them into this form and then translating into logarithmic form. Okay. If you don't remember how to do that, it means you didn't learn it. So you got to go back and learn. Okay. It means, oh, again, the most likely explanation is you're following an example without letting it sink into your head. Okay. You're following an example when you're doing a problem, when you'd already done a few. If you've already done a few, put the examples away and do it. Okay. When I design these problem sets, I generally have at least 2, 3 problems with videos that show you and reinforce how to do it. If you're still going back to the videos after that, you really need to make your best attempt at solving the problem without looking at a video or looking at what you did in the last problem. Put everything away, focus on this problem, and learn to do it. And if you can't, then by all means go back and look whatever you have to until you can do the problems. Okay. That's not the way it usually gets done in high school, because you don't have to learn it very well in high school. Yeah, especially after COVID. You know. Anyhow, this gives you 0.94 to the T equals 12.5 over 10 1/2. Now the form is B to the A equals C. We translate it. To the form. Log base B plus C equals A, because the A here is in the exponent. T is in the exponent, that's your A. You can't do anything with the T when it's here. But when you translate it here, that T comes right out and you got T equals something that you can calculate, okay? And that's the essence of this. You really need practice and drill in order to do this. Okay, so we've got log base 0.94 of 1/2 equals T. So the T equals the log of 1/2 divided by the log of 0.94. Not a calculator trick. It allows you to do log base 0.94 without thinking through this step. I want to see this step on a test. And I want you to include this step when you're working with problems. In any case, that works out. And you get looks like my 11.5 is hold up pretty well, because I'm getting something around 12. Okay. I think that might come out around 12, which means my graph just lucked out because it wasn't a good graph. Okay. And it's hard to draw an accurate graph, so you don't get a real accurate estimate of half-life from a hand-drawn graph unless you're very meticulous. And we don't really need to be that meticulous. We'll see in a minute. Okay, whichever way you do it, it apparently comes out about 11.2, which is what I really meant when I wrote out 12. See, I put 1 here and a decimal here, and I'm right. Now, I overestimated. I use the rule of 72. I probably should have used the rule of 70, which would give me 11.7. If you put it closer, but still doesn't really nail. Actually, okay. Point is, this is then your half-life. So, by pure luck, I really thought your estimates were going to be better than mine. You estimated around 10, which isn't bad if it's 11.5, because it's hard to draw accurately. My inaccurate curve just worked out better than yours. Okay. Not because I drew a better curve. Pure luck. Okay. This makes sense. Now, there's more that we can do with this. After 24 hours, we found that we have still about 2 milligrams out of our original 10, right? So what's going to happen? I'm going to take another dose. If I'm on a regimen, or I keep doing this. But now I start out with 12 grams, and after 24 hours, that's going to go to 20% more. It's going to give me about 2.5 grams at the end of that 24 hours. Okay. You'll start with 12.5 and decrease to maybe 2.6 or 2.7. So every dose, I'm kind of increasing the average amount that's going to be in my bloodstream all day. Okay. Now, if I was taking 2 5 milligram doses every day, I maintain maybe a higher. Okay. because it's like compounding. There's an analogy there, we don't have time to get into it, and we really should. In any, my opinion, piece of pre-calculus class, we do difference equations. See where this goes. Maintain, see what the maintenance level of the drug is and stuff like that. But partly in deference to the effects of the COVID epidemic on preparation. It's just not reasonable to do that. Okay. So if you plan to be an engineer, dig a little deeper. If you plan to go into heavy mathematics in your career, dig a little deeper. If not, something you really should know just for practical reasons. But you probably get through life. Okay.